Okay, we're going to use L'Hopital's rule to evaluate this limit. Before we can use L'Hopital's rule, we have to make sure that when we use direct substitution, we get one of our indeterminate forms. So with direct substitution, we would get 1 to the 8th minus 1 over 1 to the 4th minus 1. That's 1 minus 1 over 1 minus 1, and that's 0 over 0. So because we got our indeterminate form of 0 over 0, we're allowed to apply L'Hopital's rule to this limit. So with L'Hopital's rule, we'll find the limit as x equals 1, x to the 8 minus 1 over x to the 4th minus 1. And L'Hopital's rule says we can calculate the derivative of the numerator using the same limit. We would have 8x to the 7th over 4x cubed. So we're also calculating the derivative of the denominator. And now when we use L'Hopital's, now we'll apply direct substitution to get, 8 times 1 to the 7th over 4 times 1 cubed. That's 8 over 4, which is 2. So the limit using L'Hopital's rule is 2. For this problem, we want to use calculus techniques. Water leaking onto the floor forms a circular pool. The radius of the pool increases at a rate of 4 centimeters per minute. How fast is the area of the pool increasing when the radius is 5 centimeters? We're going to use area equals pi r squared for the area of the circle. And let's see. So I want to pick out the information. The radius increases at a rate of 4 centimeters per minute. This would give me dr dt, the rate that the radius is changing over time. That's 4 centimeters per minute. How fast is the area increasing? That's dA dt. And this is our unknown in the problem that we're trying to find. And when the radius is 5 centimeters, we have 5 centimeters as the radius. Now we have this geometry formula for area of a circle. The area is pi r squared. And in order to use calculus on this, I need to introduce the rates that we're given and trying to find in this problem. So we're going to use this geometry formula to introduce the rates by calculating the derivative with respect to time on the left and the derivative with respect to time on the right. So the derivative of area with respect to time is dA dt. And then on the right, pi is a constant, so we'll carry that down. We want to calculate the derivative with respect to time on the radius squared. So that will be 2r. And because our variables don't match, we have the variable of radius, and we're taking the derivative with respect to time, we have to use the chain rule to get dr dt. So now we have our formula. We can simplify a little bit more and make this dA dt equals 2 pi r dr dt. And I'm going to look back at the information that I was given. I have dr dt being 4 centimeters per minute. And I'm going to substitute that into dr dt here. I was given, looks like I left off the 5 up here. The radius is 5 centimeters. I'm going to substitute that in for r. And my goal was to find dA dt, the rate that the area is changing. I don't know that. But since I know all of the other variables, I'm going to be able to substitute in for those and solve for the one that I'm missing. So I have dA dt equals 2 pi times the radius times the rate that the radius is changing. And as I do this, I'm going to go ahead and put the units on here so I can keep track of them. This is 5 centimeters for the radius. And for the rate that the radius is changing, that's 4 centimeters per minute. So I'm going to multiply. I've got 2 times 5 is 10 times 4. That's 40, and I still have that pi there. And keeping track of the units, I've got centimeters times centimeters. That's centimeters squared per minute. So I have the rate that the area is changing is 40 pi centimeters squared per minute. On this question, we want to find the derivative using logarithmic differentiation. And I have the equation y equals x to the 2x. So to use logarithmic differentiation, we're going to introduce logs into the equation. We have natural log on the left-hand side, natural log on the right-hand side. And what this does is it allows us to use the power rule for logs. It allows us to take that log, or it allows us to take that variable that's in the exponent and bring it outside of the log. So that's going to give me natural log of y equals 2x natural log of x. So what we've done so far is algebra. And now we're going to do the differentiation part. Because we've changed this equation to having, we started off being in explicit form. This is explicit. Form, and because we took the log of both sides, it now is in implicit form. And so when we calculate the derivative on this equation, we have to calculate it using implicit differentiation. So I'm going to calculate the derivative with respect to x on the left and the derivative with respect to x on the right. And on the left, our variables don't match, so we're going to use the chain rule. The derivative of logs, we use the rule u prime over u. That's the derivative of the inside over the inside. So this is y prime over y, the derivative of the inside over the inside. And on the right, I wrote this incorrectly. Let me fix that. So that's the derivative with respect to x. And on the right-hand side, because I have a product and both factors have an x in it, I need to use the product rule to calculate that derivative. So I'm using 2x as my first factor and natural log of x as the second factor. So I've got the first times the derivative of the second. The derivative of natural log is the derivative of the inside over the inside. our inside is x, so derivative of x is 1 over x. And then the second factor times the derivative of the first. Derivative of 2x is 2. So we have y prime over y. These x's cancel out, and we have 2 plus 2 natural log of x. I'm going to multiply both sides by y to get y prime equals y times 2 plus 2 natural log of x. And the final thing I want to do is remember at the beginning our equation was written in that explicit form, y equals, so I'm able to replace that y with x to the 2x, and that's 2 plus 2 natural log of x. So we get our derivative of x to the 2x being x to the 2x times 2 plus 2 natural log of x. Thank you for checking out my videos. Have a great day.